Okay, I think this is where I stopped in the last class. Uh, so two type of special barrier for the drug distribution is the placental, another one is the blood-brain barrier. The molecules which are very small in size, they can cross irrespective of whether it is a water-soluble molecule or lipid-soluble molecule. They can cross this placental barrier. And coming to blood-brain barrier, the molecules which are smaller in size and having good lipid solubility, right? So example, uh, levodopa, dopamine. So these are the molecules which can easily cross the blood-brain barrier. So one point that you have to keep in mind is, so not all the drug molecules they can reach brain. Very important question. Very important point. Very important interview question. Not all the drug molecules can reach the brain because of the presence of very special type of barrier called as blood-brain barrier. So this is where where I have to stop, where I stopped actually in the last class, and I have to start from here. So what is this volume of distribution? Just like bioavailability, right? So we calculated F. Okay, so it represents the bioavailability. So we calculated the relative bioavailability, absolute bioavailability, percentage bioavailability, different calculations, different formula we have seen, right? So just like that, one another important parameter is the volume of distribution, which is
Sir,
represented. Yeah,
in previous class I asked a doubt regarding relative bioavailability.
I told that in Wednesday tutorial session we will solve some problem that I'll answer you. That three
Okay, sir.
o'clock class, okay.
Okay, sir.
That time I'll continue the bioavailability concept that I will discuss. Okay,
Okay, sir.
yeah. So this is a very different concept, right? So I don't want to mingle that. So volume of distribution is denoted by BD. Sometimes it is called as apparent volume of distribution. So the formula for calculating BD is BD is equal to Q by Cp. So where BD is the volume of distribution. This Cp is already we discussed about Cp. Cp is the plasma concentration, and Q is the total amount of drug molecule, or we can say simply dose of the drug molecule. So this is the formula for calculating the volume of distribution. Very important calculation in pharmacokinetics, right? So the definition for volume of distribution is a volume of fluid that is required to contain the total amount of drug in the body at the same concentration as that present in the plasma. Okay, so the definition is, the volume of fluid that is required to contain the total amount of drug in the body at the same concentration as that in the plasma, Cp. Say for example, you are taking some drug molecule. Okay, so after a period of time, you are collecting the blood sample. So from the blood sample, you are isolating the plasma. So from the plasma, say you have collected 2 ml of blood sample, and you isolated the plasma, right? Say 1.5 ml of plasma, right? So you are measuring what's the concentration of the drug molecule that is present in this 1.5 ml. Okay, say for example, you have taken 100 mg of the drug molecule, and while measuring the concentration present in 1.5 ml of the plasma, so it is like zero point 0.5 mg of the drug molecule is present in the 1.5 ml of the plasma, right? So now, if zero point 0.5 mg of the drug molecule is present in 1.5 ml of the plasma, what is the what is the amount of fluid, volume of fluid that is required to contain the total 100 mg of the drug molecule. That is what is called as the volume of distribution. Is that understandable? Should I repeat?
So can you repeat it, sir?
Okay, once again I repeat. Very simple concept, right? So let me erase this. I'm just giving example for the definition given here, right? So definition itself is very clear. Volume of distribution is one of the very important parameter normally calculated in pharmacokinetic studies. So what is going to be volume of distribution? Again, listen carefully, right? So one last time. The volume of fluid that is required to contain the total amount of drug Q of a drug in the body at the same concentration as that present in the plasma CP. So for understanding the definition, right? So you take example as you're taking a drug molecule, right? So the total quantity of the drug molecule is 100 mg, or we can say the dose of the drug molecule is 100 mg. So you're taking the drug molecule, right? So after some time, you're you're taking or collecting the blood sample. The intention of this collection is that we have to measure what is the concentration of the drug molecule that is present in the blood sample. Say you are collecting 2 ml of blood. So out of that 2 ml, right? So you centrifuge that and you collect the plasma. Say 1.5 ml of plasma is isolated. Now, in this 1.5 ml of plasma, you are estimating that what is the concentration of the drug molecule present in this 1.5 ml of plasma. Say for example, you identified that 0.5 mg of the drug molecule. 0.5 mg of the drug molecule is present in 1.5 ml of the plasma. If point if 0.5 mg of drug is present in 1.5 ml of plasma, what is the volume? What is the volume required to contain the total 100 mg of the drug, total 100 mg of the drug molecule. That is what is called as the volume of distribution. Is that understandable?
Yes, sir.
Yes, right. So that is what is called as volume of distribution. Very important calculation, right? So whenever we give blood sample for any kind of analysis or injury or disease, right? So definitely, if you are administered with drug molecule, they will calculate what is the volume of distribution of the drug molecule. Slowly, you can understand, right? So what is the need for that, right? So here this is a graph plotted between time on x-axis and the plasma concentration on y-axis. Time versus plasma concentration. So already we have seen some graph like this, right? So looking at the graph, we can say what type of administration, what's the mode of administration of the drug molecule. So anybody guess what's the mode of administration of this drug molecule?
Intravenous.
Okay, it is intravenous, intravenous, right? So in case of intravenous, we directly keep the drug molecule on the blood. So that is why at time 0, so this is the point at which time is 0, the concentration is peak, very high, which means that the entire amount of the drug molecule, the complete dose of the drug molecule is kept on the blood, right? So when time goes on, the concentration decreases. So can you tell what's the reason for decrease in the concentration? So why when time goes, the concentration decreases? What's the reason?
due to absorption.
Again, I don't know what to say.
Metabolism and its
Wait. If I say that it is intravascular administration, intravenous administration, is there anything called as absorption? I repeated this point many times. I'm going very slowly. Is there anything called as absorption for intravenous administration?
motion,
Yes or no?
motion.
No, right? So in interview and all, if you speak like this, right? So if the person is talking about intravenous intravascular administration, if you say the word absorption, no, they will conclude that you do not know the concepts. Don't get confused. Very simple. There is nothing called as absorption for intravascular administration, intravenous injection. There is no concept called as absorption. The absorption is 100%. There is no absorption. Okay, there is no absorption, right? Because we are placing the drug molecule, entire drug molecule, directly onto the blood, right? So the reason for decline here is that not absorption. The decline is here because of the distribution and elimination. So gradually the concentration decreases, which means that initially the drug molecule is present in one part of the body. So when time goes on, the distribution starts. Okay, wherever the blood goes, so to all those parts, the drug molecule can also go. That is what we studied in the previous class. So because of that, the concentration, right? So because of that, right? So molecule is now translocating, moving from one part of the body to the other part. So what will happen? The concentration will gradually decrease up to this. Up to this, what's happening is that there is a kind of distribution that is taking place. The molecule is distributed to the various compartments we studied in the last class, right? So different compartments, water compartments. So the molecule is distributed to various water compartments, other compartments in the body, fat compartment, in any compartment. So that is why gradually the plasma concentration decreases. So beyond certain point, there is no big role for distribution. Actually, this distribution process is a very rapid process because the rate of flow of blood to different organ is very fast. So distribution process will also be very fast because it directly depends on the rate of the flow of the blood. So beyond this point, what is actually happening is the elimination process takes place. So what is elimination? Maybe the drug molecule started to metabolize. Some extent we discussed about what is metabolism, right? So the molecule in its one form converted into another form, that is called as the metabolism. Also the excretion process will start. Slowly the molecule will be removed from the body. So this metabolism, excretion, all collectively contribute for the elimination phase. So there is a decline and slowly it reaches the zero. I hope you understand, you remember the graph for the oral absorption. Oral drug molecule will be something like this. So there, this is the absorption, this is the absorption and distribution, and this is the elimination phase. Okay, so the why actually this graph is shown here because when to calculate this volume of distribution. So if you take the drug molecule as intravenous injection, so can we measure, can we calculate the volume of distribution at time 0? No, because we should not, that won't give the correct value. Then when we have to measure this volume of distribution, we have to allow the molecule to completely distributed. Once if we confirm that the molecule is completely distributed throughout the body, entire body, then that point onwards we can measure what is the volume of distribution of the drug molecule. Is that point understandable?
Sir,
Should I yeah.
is this volume of distribution calculation only for intravascular mode of administration or
No, no,
also
no.
for?
For all.
Okay,
Just I'm taking this as example. Volume of distribution is what is the volume in which the drug molecule is distributed. Okay, it is for each and every drug molecule, not only for IV. Since for all the examples I have taken oral administration plot, this time I have taken another plot.
okay, sir.
Okay, this is applicable for oral administration also. Okay, clear?
Yes, sir.
Not only for oral and IV, it is applicable for all mode of administration, right? So this is a formula basically you will be using for calculating the volume of distribution for solving the problem. So VD is equal to dose of drug given IV by plasma drug concentration immediately after the distribution phase. So for this mode of administration, we can exactly calculate the not not this one, right? So we can calculate for anything. So this is for IV, right? So for IV, what's the formula for calculation? Dose of drug given intravenous by plasma drug concentration immediately after the distribution phase. This is the formula that you have to use if the problem is related to IV administration of the drug molecule. Okay. Okay. This is I don't know whether it's clearly visible for you. Is it visible?
Yes.
Okay. So if you are in laptop or computer, I hope this will be visible. If you are on phone, I don't think this will be completely visible for you. Anyway, uh, okay. So for what is our understanding is that for 70 kg male, for 70 kg men, right? So what will be the total volume of fluid, water? What will be the total volume of water?
42
It's
liters, sir.
42 liters, right? So that is what we discussed in the previous class. 42 liters, right? 42 liter. 70 kg man, right? So if we take example as what is the molecular target of aspirin?
Cyclooxygenase, sir.
Cyclooxygenase is the molecular target, right? So what we are interested is oral bioavailability. The oral bioavailability of aspirin is 68 percentage. Okay, F is 68 percentage. So what is our understanding? If we say 68 percentage is the oral bioavailability, what does it mean?
Sir, it means that 68% of the drug molecules enter systemic circulation.
Absolutely. If you take 100 mg of the drug molecule, how much quantity will enter?
So 68 mg.
68 mg will enter, right? So that is what we can understand from this figure 68. The urinary excretion is 1 percentage. We did not discuss about the excretion. Just for a moment, leave it. Bound to plasma is 49 percentage. What does it mean? Bound in plasma is
49 mg of drug molecule binds to proteins in the blood, sir.
49 percentage, not mg, right? So don't use the unit, right? So whatever is the quantity, right? So 49 percentage that has the ability to go and bound to the plasma proteins, right? So can you name any plasma protein commonly present? Albumin, any other? Any other? I discussed 4 5
Glycoproteins.
Yes, right. So that is what we can understand from this. Clearance we not yet discussed. We'll see that later. For time being, just no need to worry about clearance. So volume of distribution is what we are discussing now. We had to understand this value for few drug molecules. So we are interested in this aspirin because very commonly used drug molecule. So if we look at what is the volume of distribution of aspirin, it is 11. Okay, 11 liter for 70 kg. Units are very important. You have to memorize the units, right? So volume of distribution is liter per weight kg, right? So what we can understand from this 11 for volume of distribution? What is your understanding? We defined the volume of distribution. I gave an example for volume of distribution. Based on that, what is your understanding if we say 11 is the volume of distribution of aspirin? Yeah, somebody can try. In a class like hello, in a class like in a pandra. Okay. Yeah, somebody can respond. See, we are discussing about distribution. We discussed about volume of distribution. I gave definition. You asked me to explain again. I explained. You said that you understand what is volume of distribution. Now I am asking that if the volume of distribution is 11 liter per 70 kg for aspirin, what does it mean?
Sir, I think it is the volume of plasma required to contain the entire drug molecules.
See, plasma is only one compartment. Am I right or wrong?
Yes, sir.
Okay. So now you tell the answer. What you
Maybe it
said
is a
is wrong.
total volume of body
Yes,
compartments.
total volume of body compartment that is needed for that is required. Okay, the dose is not given. I don't know. Dose is not given here. Yeah, maybe that's a common dose. So 11 liter is needed if you take 11 liter of the fluid is needed for a 70 kg person. Is it understandable? We have 42 liter, right? So out of that 42 liter, if we measure, so 11 liter. In 11 liter, we can find this aspirin molecule. Is that understandable? But I'm going to confuse you now. So if we take this drug molecule, chloroquine, okay, literally I'm going to confuse you. You have to tell the correct answer, the logic answer. If we take chloroquine, so this chloroquine is a anti-malarial drug molecule. It's a natural compound, anti-malarial drug molecule. So it's having 89 percentage of oral bioavailability. Is it good? 89 percentage of oral bioavailability.
Yes, sir.
Yes, right. Before that, we take this as example. One more question, right? Samphotherizin, there is no value given for oral bioavailability. What is the reason?
So maybe it is IV.
It is not administered orally. Maybe some other route of administration, right? So maybe IV most probably. So coming back to this chloroquine, it's having 89 percentage of oral bioavailability. Then plasma binding is 61 percentage. So we are interested here. So what is the volume of distribution? What is the volume of distribution?
13,000.
11 liter per 70.
13,000, right? So 13,000 is the volume of distribution for the anti-malarial drug molecule chloroquine. Okay. So 70 kg is the approximate weight of the men. For 70 kg person, 42 liter water content will be there. So how come the volume of distribution value is 13,000 for chloroquine? Is my question understandable?
Yes, sir.
The 70 kg person itself, they used to have 42 liter. 100 kg means you can proportionately increase the 50 55 liter water. So how come for chloroquine the volume of distribution is 13,000 liter per
So
70
maybe
kg?
the dosage of administration has uh, higher units, right?
Even if it is higher, how come this value will be 13,000? We are we are not considering what is the dose. We are considering about what is the volume that is required to have the drug molecule. 13,000 liter. So do you think that it's possible for a person to have 13,000 liter of water?
No, sir.
Are you able to understand my question? Whatever is the concentration doesn't matter. Is a person going to have 13,000 liter of water? If not, why the value is very larger for chloroquine? What's the logic?
Sir, only a part of the drug will be contained in the body, so only for 42 liters.
So can you give example?
With just 42 liters, we can feel the therapeutic effect. So it is high.
Okay, I just give the answer for this question, right? So there are certain drug molecules. They will have a very larger volume of distribution, VD, just like chloroquine, right? Which doesn't mean that the person is having that much volume of water in the body. That's not at all possible, right? So the question is that why some drug molecules have larger VD than the total body water, which is 42 liter approximately for 70 kg men. The reason for this is the drug is concentrated intracellularly. Okay, so which means that the concentration of the drug molecule, we make the calculation VD based on based on the amount of the drug molecule that is present in the plasma. If very few quantity of the drug molecule is present in plasma, if large quantity of the drug molecule is present inside the cell, so this is a cell, large amount of the drug molecule they entered into the cell. Okay, very few quantity is present in the plasma. So this is the plasma, very few quantity is present, more quantity is present inside, right? So if we estimate this calculation based on the concentration of the drug present in plasma, very few quantity, again I repeat, very few quantity is present in the plasma, larger quantity is present inside the cell. If this is the case, that will lead for very larger VD value, even much higher, more than the total body water. That is why the value for chloroquine is very larger. It is 13,000. Okay, which indicates that very lesser quantity of the drug molecule is present in the plasma, and more concentration of the drug molecule they entered into the cell. Is that understandable?
Yes, sir.
Now if you go through this formula, you can understand. Okay, so Q is the total concentration dose of the drug molecule, Cp is the plasma concentration. So if the Cp value is very less, okay, which means that this value Vd value will be very large. So which means that more and more quantity of the drug molecule is now present inside the cell. That is one of very important question related to any competitive examinations, right? So that's the reason why the plasma constant, why the Vd value is much larger for certain drug molecules like chloroquine. Uh, this is a pH, right? So quickly just
Sir,
note down. Yeah,
do we have to memorize the values that is shown in the previous table?
which table? No. You should know the logic. Okay,
Okay, sir.
no need to memorize any values. You have to remember the unit, and for one or two drug molecules, if possible, you can remember. That is always good. If they ask to explain the volume of distribution, right? So you can give example as chloroquine. You can yourself tell that why chloroquine is having very larger VD value.
Okay, sir.
It is not necessary to remember everything, memorize everything. That is not possible. That is actually not needed. If possible, for one or two common drug molecules, you can remember the value, at least the approximate value, right? So these values you please note down, the pH, right? So this is very important. Um, Even for solving that previously studied problem, we related pH and pKa. So I asked naproxen, right? So I think I gave stomach. I think stomach or intestine, blood. No, plasma, right? In the examination,
Yes, sir.
yeah, plasma, right? So the plasma, you can take the value almost. All part of the body it is given. Gastric acid, the pH is 1. Lysosomes, the pH is 4.5. Uh, Granules, chromaffin cells, pH is in the range of 5.5. Skin, the pH is 5.5. Urine, the pH is 6. Neutral pH 6.81. Cytosol is 7.2. Cerebrous spinal fluid is 7.3. Blood 7.34 to 7.45. Mitochondrial matrix is 1.5. Pancreas secretion is 8.1. So this I strongly recommend you to memorize this. Remember this value for the examination. Again, I repeat: if I set the question paper, or if they want to make the question paper simple, they will tell what is the pH of the biological compartment. They will give the pKa of the drug molecule. If any other setter outside the Shastra is setting the question paper, we cannot expect the same thing. We cannot blame them, right? So it is necessary to remember all this: the pKa of all the important functional group and the pH of various compartments of the body, right? Okay, that is about distribution, and we have to solve some problem related to distribution. So better, you know, I think we have another 15 minutes. I go for the next topic, right? So after finishing the metabolism and finishing the excretion, combinedly we'll solve the problems related to absorption, distribution, metabolism, excretion. Few problems, right? So coming to the next topic is the biotransformation or metabolism. So already I defined in my own words what is meant by metabolism. Metabolism is the process by which the drug molecule in its original structural form will get converted into other form. That is what is called as the metabolism. Important point is it is an enzymatic reaction. So almost all the metabolic reactions taking place with the help of some enzymes. So I hope you completed your biochemistry. You know the main function of enzyme. So they act as biological catalyst. So the substrate molecule will go and bind to the enzyme, where it will be converted into the product. So the main job of enzyme is converting the substrate into product. So here in case of drug design and the concept of medicinal chemistry, so the substrate is the drug molecule. Drug molecule, it goes and binds to some enzyme. Very specifically, I said that there's a family of enzyme called as cytochrome P450 to which they bind, and drug molecules are the substrate for the cytochrome P450, and the cytochrome P450 will convert the substrate molecule, drug molecule, into the product. The products are what are called as metabolite. The products are called as metabolite, and the entire process is called as metabolism, right? So biotransformation, translocation, transformation, two different terms. So far we discussed about absorption, distribution. Okay, these are something related to translocation, related to movement of the drug molecule within the body. So out of the four parameters which we study in pharmacokinetic, the only one parameter that is related to transformation, which is conversion from one form to another form, is the drug metabolism. That is why it is called as biotransformation. So biotransformation, metabolism is nothing but a metabolic conversion of drug molecule to more water soluble metabolite that are more readily excreted. Very important, right? So we know why the absorption is taking place. We know the scientific reason for why it is taking place. We know the scientific meaning for why the distribution is taking place, right? So you may have a doubt why this biotransformation is needed. The molecule can directly excrete it without the biotransfer. Why this process is actually taking place? The reason is that, many times I repeated, a good drug molecule should have solubility in both water and lipid. So we expect the molecule to have more water solubility. A good drug molecule will have comparatively more water solubility than, sorry, more lipid solubility than water. But it should have both lipid solubility as well as water solubility. First thing, this water solubility plays important role till the molecule reaches the circulation. So once if the molecule reach the circulation, then the molecule should enter into the cell. For entering into the cell, the important solubility is the lipid solubility, right? So since the drug molecules are having more lipid solubility, they can easily enter into the cell. If the molecules are more lipid soluble, which means that less water soluble, the molecule cannot easily excrete it from the body. For the excretion, we need, for the absorption, we need more lipid solubility, and for the excretion, we need more water solubility. As of now, the drug molecule is present more lipid soluble. It cannot easily excrete it from the body. Any foreign compound that enter into the body should come out. If it does not come out of the body, they will reside in the body for a long time, so which will give unnecessary unwanted side effects. So drug molecule is a foreign compound, it's an exogenous compound. So once if you take the drug molecule, after executing the biological response, the molecule should come out of the body. For coming out of the body, the only way is excretion. There are different route of excretion, we'll discuss that later. For excretion, we need more water solubility than lipid solubility. The drug is lipid soluble, but we have to convert that drug molecule into more water soluble to make it more easily excreted from the body. And that is the reason why there is a process taking place called as biotransformation. The more lipid soluble compounds will be converted into more water soluble compound. That's the scientific reason why the biotransformation or the metabolism is taking place, right? There may be three situations during the process of biotransformation. So we have the original drug molecule. Say the drug molecule bind to some cytochrome P450 enzyme. Okay, so it converted the substrate molecule, drug molecule, into some product or products. Most of the time, products. So the initial drug molecule in its active form, the metabolites, it may be inactive. The first case is the initial drug molecule is in its active form, its metabolite after the metabolism by cytochrome P450 enzyme. The metabolites, it may be inactive in nature, which means that the metabolite cannot produce any biological response, desired biological response. The second situation is that the initial drug molecule is active. So the drug molecule is the substrate molecule for the cytochrome P450 enzyme, goes and binds to cytochrome P450 enzyme. where the P450 enzyme convert the substrate molecule into the corresponding product. In our case, those are the metabolites. There are cases in which the metabolites can also be active in nature. Again, I repeat, there are cases in which the metabolites can also be active in nature. The third case is the initial drug molecule is inactive. Very rare, very interesting case. The initial drug molecule. While taking the drug molecule, we take the drug molecule in its inactive form. So the drug molecule is the substrate for cytochrome P450. It goes and binds to cytochrome P450, and cytochrome P450 convert the inactive drug molecule, that is a prodrug, into active drug molecule. So these are the three possible things that can happen due to metabolism. Is that understandable?
So, can these kind of biotransformation reactions can be
Sorry,
reversible, sir?
can you say again?
So, can these kind of reactions be reversible, sir?
No, it is not reversible. They are not reversible. Only one direction. The arrow mark is only one single headed. They are not reversible. It cannot go in the reverse direction.
Yes, sir.
Once if the molecule is metabolized, we cannot get the original drug molecule again.
Yes, sir.
Okay, don't get confused with the drug molecule binding to the receptor to form the drug receptor complex. So here we use the double-headed arrow, forward and reverse, right? So this is the association, and this is the dissociation. The backward is the dissociation, forward is the association. That will not happen in case of the CYP450.
Yes, sir.
Okay. Yeah, any other questions? One more point is the most of the drug biotransformation takes place in the liver. So can you tell the name for the biotransformation taking place in liver? What is the name for the biotransformation taking place in the liver?
Detoxification.
What is the name? Name. We had one separate slide for that.
Drug metabolism, sir.
We are talking about metabolism. What is the specific name of biotransformation that is taking place in liver? We studied some effect and all.
First pass effect, sir.
Yeah, first pass effect, right? That is what we studied as the first pass effect, which is nothing but the biotransformation that is taking place in the liver, right? But also drug metabolism, the enzymes can be present in different tissues like gut, kidney, brain, lung, skin. That is why while talking about the first pass metabolism, the major site for the first pass metabolism is the liver, but not necessarily it should take place only in the liver. It can take place in gut or kidney or brain or lung or skin, anywhere it can take place, because almost all the tissues we have some enzyme which can metabolize the drug molecule, right? So that is few words about biotransformation. Any question up to this I can answer. I think we have another 3-4 minutes time.
Sir, so a drug molecule can either be broken down into inactive metabolites or active metabolites.
Yes, we can. So next class I'll be giving some example for a drug whose metabolite is active, drug whose metabolite is inactive. A few examples for the drug molecule initially in its inactive form converted into active form after the metabolism.